Welcome back to the course entitled Symmetry, Stereochemistry and Applications. In the initial few lectures, we have discussed about nomenclature of organic compounds, symmetry elements and point groups that can be derived for different small organic and organometallic complexes. So, with that brief introduction to the molecules and symmetry nomenclature, today we would like to start discussing about the second part of the course, where we will talk about the conformational analysis of organic molecules. So, here in this series of lectures, we will talk about Neumann projections, ring strain and cyclohexane conformations in next few lectures. So, the first question that we would like to address is how to describe a molecule. Molecules are generally described by the bond distance and bond angles and torsion angles, that is the dihedral angles between the constituting atoms in the molecule. And once you know the bond angles, bond lengths and torsion angles of a molecule, then we would also like to know how those atoms are oriented in space to know about their stereochemistry. So, for example, for simple molecules like hydrogen, which we all know that is a linear molecule. So, for a simple molecule like hydrogen, it is sufficient to know the distance between the two hydrogen atoms, that is the bond length between the two hydrogen atoms. Then if we think of having a linear molecule like HCN, which is written like this, we have a single bond and a triple bond in this molecule. So, we need to define or know the distance between the hydrogen and carbon, and we need to know the distance between the carbon and the triple bonded nitrogen, and also we need to know the angle between hydrogen, carbon and nitrogen. Then only we may be able to say that this molecule is linear if this angle is 180 degree. We have a simple molecule which we all know is water, is also a triatomic molecule. So, here what we need to know are the distances of hydrogen to oxygen and the angle HOH, that is this angle, which from spectroscopic data we know is about 104 degree. Then the concept of torsion angle or dihedral angle comes when there are 4 atoms connected in a sequence. So, for example, one can draw a butane like this, and the same molecule like this. What is the difference? The difference is the torsional angle about this bond. So, the angle between the planes formed by the atoms 1, 2 and 3 and 2, 3 and 4. So, the angle between the plane formed by atom 1, 2, 3 and the plane formed by two, 3, 4 is called the torsion angle. How to understand this torsion angle easily is to draw a molecule which we all know is hydrogen peroxide. So, in hydrogen peroxide, if we draw the 3 atoms, 1 hydrogen and 2 oxygens like this, and the 4th hydrogen, 4th atom or the 2nd hydrogen is coming here, So, the way we have drawn it is those two oxygens and this hydrogen is in the plane of the projection, and the other hydrogen along with the two oxygen is above the plane of the projection like that. So, the angle between these two planes is the dihedral angle in this particular molecule, that is the angle about this OO bond. So, when we have a molecule which has more bonds, so you have more number of different bond angles and then you have more number of different torsion angles. So, to describe a molecule, one has to know all the possible bond lengths, bond angles and torsion angles. So, when we try to write or draw the molecule in a two-dimensional plane, we would like to know how those atoms are oriented in 3 dimensions. We need to understand the difference between conformations and configurations. Conformations are different possible 3-dimensional arrangements of atoms within a molecule. These different 3-dimensional arrangements are interconvertible without breaking or making any bond. So, what do we mean by that? I will again take the example of butane. The way I had initially drawn are two different ways, either this or that. So, the torsion angle about this and the torsion angle about that bond are different in these two different ways of representation, and these are called the conformers. Conformers, that means they are related by an angle twist, and one can be easily interconverted to the other without breaking or making any bond. Some other examples are the examples of cyclohexane, which will be the part of our discussion towards the next few lectures in this course. So, one can draw cyclohexane like that, one can draw a cyclohexane molecule like this, and one can draw the cyclohexane also like that. So, these are different conformers of cyclohexane. These different forms can be interchanged by bending or twisting the molecule, and these conformers are temperature dependent. At lower temperature, the conformation which has lower energy is more stable, and at higher energy we start seeing different conformations of a given molecule. What are configurations? Configurations are different possible 3-dimensional arrangements of atoms within a molecule. These different 3-dimensional arrangements are not interconvertible without breaking or making any bond, and one arrangement can be converted to other by breaking and making bonds. So, let us take one example. A very simple example is a compound like this, which I am drawing here. It is a derivative of ethane, one bromo, one chloroethane. So, the way I have drawn here is that this bromine, the carbon atom and the hydrogen are on the plane of this board, and the methyl group and the chlorine are respectively above and below the plane of this board. A different configuration of this molecule is being drawn here, where I have the in plane atoms as it is, but the groups which are above and below the plane are drawn separate in a different way, and what we see is the chlorine which was below the plane has come above the plane, and the methyl which was above the plane has gone below the plane, and these two cannot be interconverted without breaking or making any bond. So, these two different orientations or arrangements of this molecule are called the configurations of one particular organic molecule. The other type of example of configuration can be seen in geometrical isomers, where we have the cis and trans isomers. So, the trans compound would look like this, where the two chlorine atoms are in the opposite side of the double bond and the two hydrogens are also opposite. So, these two geometries, these two different orientations are two different configurations of the same molecule, but they are not interconvertible without breaking or making a bond. So, these are the configurations which are not interconvertible without breaking or making a bond, whereas the conformations are interconvertible without making or breaking a bond. So, now what we would like to draw are different views of ethane. So, here what I have is a model of ethane which you can see, and this model of ethane has 2 carbon atoms and then 6 hydrogen atoms connected on either side. So, the way I am trying to draw, I am trying to see the molecule like this and trying to draw it on the plane of the board. So, in this particular molecule, what we need to know are the distance of the carbon-carbon bond, distance of the carbon-hydrogen bond, and the angle HCH and also the angle HCC. So, the ideal bond length is about 1.54 angstrom for ACC single bond. Ideal bond length for CH single bond is 1.10 angstrom. These angles are tetrahedral angles, so they are close to 109 degree. And if we know these parameters, then one can identify or draw the molecule in 3 dimensions. So, the way I have drawn this molecule is called the Schauer's projection. This molecule, as I have shown here, it is like a ball and stick model, and in this ball and stick model, the way the molecule is drawn on the board, I am doing it here. The bigger atoms are my carbon atoms and the smaller atoms are the hydrogen atoms that are present in either carbon atoms. So, this is called the ball and stick representation or projection. The third way of drawing a similar the molecule is to draw hard sphere object. So, the carbon in the front is drawn as a big sphere, carbon at the back is partially drawn like that, as if it is behind the molecule, behind the first carbon. Then you have 3 hydrogens which are smaller in size but occupies a certain volume is drawn like that. These hydrogens are on the front carbon, so that is why we see them as full atom, and the ones which are connected to the backside atoms are only seen a part of it, and we only draw that like this. So, this is called the space fill model. So, in your textbook you will see this type of different models or projections of the same molecule for different purposes. So, now we would like to draw your attention to a method which is called the Neumann projection, how Neumann projection can be drawn for different molecules. So, we will start with the molecule ethane. What we have shown in the previous slide or previous drawing is we had drawn ethane using Shawhorst projection, which is like this. I have the hydrogens, so in this projection, if we try to now look at the molecule from this side, so what we are trying to do is trying to see the molecule from that side. So, when you are trying to see the molecule from the side of one carbon, what you see, the front atoms are projected towards you and the hydrogen on the back carbon is projected towards me. So, this projection, when we try to draw on a two-dimensional surface or on the plane of the board, what we draw is as a big sphere or a big circle represents the front carbon. The three hydrogens that are present on the front carbon are drawn at 120-degree angle with respect to each other, and the hydrogens which are at the back carbon is behind. So, we draw it with smaller sized bonds following the same trend. So, this way of representing a molecule is called the Neumann projection. So, now suppose if you have different atoms present in this molecule instead of just two hydrogens, suppose I replace the hydrogens by two bromine atoms which are shown here in red, then the molecule would look like this. I have two bromine atoms and two hydrogens on each carbon, and the molecule is like this. So, if I try to draw this molecule in Neumann projection, how should it look like? In the front carbon I have a bromine, and as you know, the carbon bromine bond length is much larger than the carbon hydrogen bond length. So, that should be represented, and the back side also has bromine like that, this hydrogen, and here is another hydrogen. So, now if I try to rotate the back carbon like that, so I reach a different conformation. So, how do I represent that different conformation is shown here. I write the front carbon as usual. The bromine atom in the front carbon is at the top, the hydrogens are on two sides as it is, but the bromine on the back carbon is now at an angle 60 degree with respect to the initial condition, and the hydrogens are also dispersed like that. So, now if I try to again rotate this further by another 60 degree, which means I am doing it like that. So, now what happens is behind this bromine I have hydrogen, behind that hydrogen I have a bromine, and these two hydrogens are one behind the other. So, if I try to draw the Neumann projection of this particular compound, keeping the front carbon unaltered, it would look like this. And then further, if I rotate this bond by 120 degree, sorry 60 degree, what should I get? The back carbon is further rotated by 60 degree to make it look like that. So, one bromine is up and the other bromine is down, and the hydrogens are in between. So, if I try to draw that on this projection, I would get something like this. So, what we have learnt now is to draw different conformations of a molecule using Neumann projection, and when you rotate the molecule, rotate the atom about a bond, you get different conformations. So, these are different conformations of 1,2-dibromo ethane, and that 1,2-dibromo ethane conformations are interconvertible without breaking or making any bond. Just by rotating the CC bond, you are able to draw different, you are able to make different arrangements of those atoms just by rotation. So, these are conformations, not configurations, and these are very important in various organic reactions, which we will see at a later part of this course. So, what we have learned by now is that using Neumann projection one can identify different conformations, and we have names for those different conformations. So, when the molecule is like that, when the hydrogens are one behind the other, or in case of dibromo, when the bromine is behind bromine, hydrogen is behind hydrogen, that conformation is called the eclipsed conformation, and the second one, in case of ethane, when the hydrogens are not one behind the other, rather they are at an angle 60 degree to each other, is called the staggered conformation. Here the dihedral angle, that is theta, between the hydrogen carbon carbon hydrogen group is 0 degree, and here the dihedral angle is 60 degree. So, the two different Neumann projections of eclipsed and staggered conformation are shown here. If we draw those as a Schauer's projection, we should be drawing them like this. This first one that I am drawing is the eclipsed conformation, and the second one that I am drawing here is the staggered conformation. So, what we have learned by now is there are conformations which are different spatial arrangements that a molecule can adopt due to rotation about a sigma bond. A staggered conformation is a low energy conformation where the bonds on the adjacent atoms bisect each other, that is the dihedral angle is 60 degree, and it maximizes the separation between the atoms in the adjacent atom. And eclipsed conformation is a high energy conformation where the bonds on the adjacent atoms are aligned with each other. So, for example, here in this case of dibromo ethane, this concept of high energy and low energy can be understood easily. When the molecule is drawn like that, where two bromines are one behind the other, these two large atoms have steric hindrance. As a result, this molecular conformation is unstable, it is of high energy. When you rotate the back carbon by 60 degree, the distance between the two bromine atoms increases. As a result, the steric hindrance between the two bromine atom is reduced. So, this particular staggered conformation is having a lower energy compared to the original fully eclipsed conformation. But then when we rotate this molecule by another 60 degree, we reach another eclipsed conformation where there is bromine and hydrogen one behind the other in two different occasions, and this is called partially eclipsed, and this also is one of the higher energy conformers of dibromo ethane. And if we rotate the bromine, this back carbon, by another 60 degree, we reach a conformation where two bromines are exactly opposite, and this conformation is the most stable conformation where the steric hindrance and the torsional strain is the minimum. So, we call it as anti-conformation. So, in the next part of this lecture, we will continue from here and discuss about various conformations of ethane and substituted ethanes.